Time-appropriate greetings, ladies and gentlemen, and welcome to Lab 2. We have a number of topics for you today. First, you're going to have the chance to get a little bit more practice with the C programming language by creating an abstract data type. And I think you're going to find that pretty helpful because it's a very similar assignment to what you're going to be working on for homework. Second, and something I'm going to be spending most of this presentation talking about, we're going to cover essentially a meta topic, learning how to learn Unix. And I'll get into what that exactly means in a little bit. And before I do that, I'd really like to address something that I should have done last week, which is introduce myself. So you've likely figured out my name at least. I'm Sean McBride. And just a little bit about my background. So I grew up as a pretty nerdy kid in the San Francisco Bay Area. And one of the cool things about growing up in a very tech-heavy area like the San Francisco Bay Area is you can have tech lineages to some degree. So my grandfather actually, after the Korean War, used his GI Bill to get training in IBM mainframes from UC Berkeley. And then he worked as a mainframe operator for a number of Silicon Valley companies, such as Ampex, throughout the 1960s. My personal first exposure to computing was really when I went with my great aunt to bring your son or daughter to Workday, and that was held at Amdahl, a now defunct Silicon Valley tech company. The cool thing about that event was I was about 7 or 8 years old, so pretty impressionable, and I had a chance to just basically be plopped in front of a Unix terminal running a session connected to a mainframe running UTS, which was a proprietary Unix operating system ported to the IBM mainframe. I also remember, in addition to playing games on the Unix terminal, sitting in a presentation where some folks in suits were talking about this really exciting thing, the World Wide Web. And they were talking about hyperlinks and they were talking about linkable documents, and it was beyond me. I couldn't really understand what they were saying. When I heard World Wide Web, I was thinking giant spiders. So nonetheless, from that event, I really got into computing, and by about 1996 or so, I had advanced to the point where I was really ready to have my first home computer. And my first home computer was something that was kind of like a Star Wars lightsaber in my case. I purchased the individual parts from swap meets, which are called computer shows and sales in the Silicon Valley Bay Area, and I assembled the pieces together. In about 1996, I installed Windows 95, and I was off to the races. A couple of years later, that turned into a paid gig for me. I was making about $10 an hour doing IT desktop help support for my public school district. And that experience doing frontline IT desktop support has been something that's been tremendously helpful throughout my entire career. And it's even been really helpful for this course because I've helped out a number of you just getting your VM set up and things like that. Eventually, my interest sort of shifted from more technical interests to the military. In particular, after the September 11th attacks, I decided that I wanted to join the armed forces. And that ended up resulting in my decision to apply to West Point, where I was accepted. While I was in the military, I was able to do a number of really interesting things, including a semester exchange program with the German Military Academy in Hamburg, Germany. I got some pretty funny sounding German awards, including the Leistungsabzeichen and the Schützenschnur. So bonus points if you know what those mean in German. Since leaving the Army, I've been in tech for about the last 10 years. I've worked in and around the IBM mainframe doing Java and Linux type work, which is kind of eerily reminiscent to some of the technology that I encountered in 1993 at Amdahl. I've done cloud migration IT architecture work at the FAA, a government agency, and I've done full stack development at a DC startup. I'm currently working in in Gabe's lab doing WebAssembly research, really outside of WebAssembly outside of the browser, so applied to all sorts of different systems. I've been married for about a decade. I live in Old Town Alexandria. My hobbies include strategy games, horror movies, and all sorts of history. So I've gotten a number of LinkedIn requests from some of you students, and I just want to say I definitely welcome that. So if you want to connect with me and you're interested in things like LinkedIn skills endorsements for C, Unix, Linux, all that kind of stuff, I'm happy to provide those. Additionally, if you're writing technical blog posts or releasing interesting pieces of open source software and trying to promote that stuff on Twitter, I'm happy to retweet as well. If there are any questions about anything in my background, I'm happy to open up some sort of AMA thread on Piazza or Discord. So finally, moving on to the actual topics. So we're going to really be talking about learning how to learn Unix, and hint, 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 we're not talking about using Google search engine here. We're really talking about how to use the tools that Unix provides to be able to learn how to use that Unix programming environment. And the core of that is something that's called the Unix Programmer's Manual. Once I get through all that, we're going to have a chance for you to practice a C abstract data type by building a linked list. So when we talk about Unix documentation, we need to really start with the Unix Programmer's Manual, which is a programmer's manual written by Thompson and Ritchie, the two creators of the Unix operating system. And the initial release was released alongside version 1 of Bell Labs Research Unix in 1971. And on the right hand of my terminal, you can see here a picture of Dennis Ritchie. Dennis Ritchie died, unfortunately, a couple of years ago, around the same time as Steve Jobs. And I personally think he was a lot more impactful for computer science writ large than Steve Jobs. And that included things like Unix, the underpinnings of macOS and iOS, and the C programming language, which was the underpinnings of Objective-C, which were used to write all sorts of Mac apps until very recently. So Unix Programmer's Manual was written by the first two Unix creators in 1971. And one of the really cool things about that is you can pull up the 1971 manual. It's available on the web. And you can take a look and see how it's organized. And you've got these different 7 sections. And to be honest, this is actually quite familiar to anyone that uses Unix documentation today. So here's 1971, and I'm going to step forward to the 2020 equivalent. Here's 2020. And so what you might kind of notice here is we've got 2 additional sections. We're not using Roman numerals anymore. And really the only other difference here is that I can see is in 1971, Section 3 is called subroutines. In 2020, Section 3 is called library calls, because subroutines is kind of like an old-fashioned type of term. But otherwise, I mean, the organization is pretty much the same. That's pretty neat, I think. So to see this documentation, I used a command, man. So man is short for manual, and to get a manual entry about the manual itself, you type in man. And that brings up the man page for the interface to the reference manual. And so we can see here in the description, we have sections 1 through 9. And this just basically gives us an idea of what a manual page looks like. We have essentially standardized sections here: name, synopsis, description, and all sorts of other things. So the trick is really to know how to get to the pages that you really care about and that deal with kind of whatever context you're working in at that time. The key commands for really making that all happen are the commands that I have on the left side of my screen now. And the main one I really want to point out is this command apropos. And that's really the way that you do a keyword search across all of the entries inside of the manual. So for example, if we can imagine I'm writing like a C program and I can't quite remember what's the function that I need to do to be able to take the length of a string. An example command I might run would be apropos string and length. And what this does is this creates a keyword search, and it takes the union of the two keywords. So this is searching for entries that use both the word string and length. And we get a pretty short list of matches. And these are all honestly pretty good at this point. So now we've got 6 things. We can kind of take a look. We've got calculate the length of a string. Hey, that sounds like the entry we want, man. Sterling. And there we are. And now we have all the information we need, including things like return length. One thing I want to point out in here is we also have this section C also. And oftentimes these are related functions. So if you don't necessarily find the result you want in apropos, if you pull up the man page of the closest thing that is similar, oftentimes in the C also you might find a better match. So if you look at the results here, you can see the name, and this is the name of the man page entry, which is usually also the name of the system call or the library function or the command you run in the shell. We have this number here, and the number relates back to these sections that I mentioned. So here for section 3, we're talking about library calls. So these are really kind of clib library calls, or things that you would run when writing a C program. The other sections have different sorts of things. So for example, there's a command that printf that's pretty commonly used to do structured string output in C. But there's also a printf that you can run in bash scripts and run from the bash shell. So sometimes it's kind of like, well, which one do you mean there? And we have another command here, what is, that is useful for that sort of thing. So if we do what is printf, we get the 2 entries that match. One is in section 1, and we know from this list before that section 1 is executable programs or shell commands. So these are things that I can directly execute and run through the shell or a shell script. Section 3 are library functions, which, as I mentioned before, really mean like C library functions. And that's important because if I was writing a C program and I wanted to look up printf, I probably would type something like man printf. And unfortunately, that defaults really in order of these sections here. So if I run that, I get printf for the shell, which we can see up here, printf section 1, not printf for libc. But we go down to C also, and we can see printf 3 there. So it takes a little bit of muscle memory and getting used to finding the information you care about, but generally it's not too bad. I want to go back up to that apropos string search query here, and I mentioned this was a union query. So if I didn't have this and here, the difference is I'm basically going to have a looser query that's either going to match on all the entries that have either the word string or the word length. And we can see here the previous union query had 6 results, and this is going to have a heck of a lot more, right? So when you get like all these entries, you really don't have a good shot of being able to get the man page that you care about. So making sure that you know how to issue the right type of query, including things like union queries, and including other options like being able to use regular expressions. If you want to know how to do regular expressions, you can do man apropos, and take a look in here to see how to do that. So that's essentially Unix documentation in a nutshell. As I mentioned, all the different man pages have kind of standard sections. Some sections have have special things like return values like that. That makes sense for system calls or libc library functions, but it doesn't make sense for other things necessarily. Or things like errors, which describes the values that the errno global in a C program could be set to that you have to do checking for. That doesn't necessarily apply to other sorts of programs. So I want to take a little bit of a sidebar and talk big picture about the anatomy of interactive Unix, because I showed a lot of documentation for Unix commands, and there can be a couple of surprising footguns. For example, the ls command lists entries inside of a directory, and it's pretty clear cut there. We can do ls, we can do a man ls, and we get the documentation there, and we see what's in section 1, so we know this is a shell command, so that's all good. Oftentimes another command one would use to basically manipulate directories and files is the change directory command. So cd ... takes us up to the parent directory, cd pres can take us back, and that's great. But it's like, okay, what if I wanted to look at documentation for cd? Well, can I do man cd? There's no entry. That's weird. Okay, let's scroll back here, take a look at our other commands. Okay, what is cd? Nothing appropriate. It's weird, right? Okay. Well, what if I do a search here? Apropos change and directory. Okay. Well, what do we have here? We got change access control list of a file or directory. That's not quite right. We have a system call change working directory. That sounds good, but that's not something we can just execute in the shell. So not quite. I mean, I guess we can take a look at change directory here. Change working directory. Right. Pretty puzzling. Go down here. We see also get CWD path resolution. Yeah. So weird. And like probably if you just kind of knew everything that I taught so far, you'd spin here and you'd be really confused why you don't have a CD entry in the documentation, because everything else is pretty darn well documented. Well, that has to do with kind of the difference here in how an interactive Unix command actually runs. And we really have two different ways that can work. The first is essentially how ls works, which is, as before, I type in, well, first our executable shell program bin sh prints our shell here, and in this case it's got my name and the computer name and the current directory and then a $sign, right? And then it waits for my input. I type in ls like I've done here, and then I execute that. And then behind the scenes, in that like split second there, the shell does a bunch of stuff here. So first it checks for something called built-ins, which I'll talk about a little bit more later. But here, when the shell checks built-ins, it doesn't find one that matches ls, so it moves on. Okay, well then the shell looks for binary files in my path. And my path is a special value, which I can show here. The path is basically a string representing all sorts of directories, and all of those directories are searched for executable programs whenever I type in a command. So when I type in ls, my path is searched, and we can see how that matched using the which command, which ls, and the executable is in /bin and then ls. And so the bin directory is in my path, and that's where the ls was found. So ls was found here. And then the shell calls fork, and then it calls exec base, or it the shell calls fork to create a new process, and that waits on that child process. And then the child process calls exec, and that loads the ls executable into memory. The ls executable makes all sorts of system calls, including open, fstat, read, close, executes printf or something like it, that executes write, and that's how we get all of our output here for ls. Cool. And then it returns back to the shell, which awakens after running wait and restarts the infinite loop to print out back to our terminal here. So just to kind of hit the point about forking and execing, we're going to get a lot more into this later on in the course, so don't stress about it too bad. But I can run another command to give you an idea of what that sort of looks like. So if I run ps/f, this is a command that essentially lists out the processes. And we see two processes. The first here is my bash process, which is the process running my interactive shell here that I'm interacting with. And the shell is doing things like printing text back out and taking my input. We also see this PSF, which matches basically the command that I ran here. And it's running in a different process. So PS is, again, one of those executables located in the bin directory found in my path. And so that's executed by creating a child process. And we can see it's a child process because we can look at this PS entry and we see the process ID here. And then we see ppid. Ppid is the parent process ID. And the parent process ID of PS is the process ID of my shell. So the shell is the parent. PS is the child here. And that's basically how that's working. So that's how ls works and how most commands work. And all the commands that work that way basically are documented more in a man page. So you can use apropos and man and all that sort of stuff to get documentation for it. But CD works a little bit differently. So earlier I mentioned this idea of something called a built-in. And it turns out change directory is actually a shell built-in. And a shell built-in isn't a separate executable. It's a set of functionality that's actually hard-coded inside of the shell itself. And so when you can imagine inside the shell loop, when it takes the input, it's got maybe a couple of like case statements or conditionals that check the string that I've entered. And if the string that I've entered matches one of these built-ins, such as CD, instead of looking at the path and searching for executables, it just captures that and it executes a function, callable function inside of the shell executable itself. So that functionality is built into the shell, so it's called a shell built-in. And shell built-ins are documented a little bit differently. So the facility for that is help. And if I run help, I can see a list of all the shell built-ins. And that includes CD here. And that includes other things like true or false. These are things you would use when writing like a bash script, for example. So we've got the list of all the commands here, and we can also do things like help CD. All right. And the documentation is structured a little bit differently from a man page, but we get more or less all the things that we care about there. So you might be wondering, like, okay, that's good that I know that there's a distinction between shell built-ins and separate executable programs that would have their own documentation via a man page, but how would I necessarily know that, right? Well, I guess you could check this list here, type in help and look through this list. It's alphabetized, see if it's on there. One other thing you could potentially do is the type command. So type will actually basically tell you if something is an executable a alias or a shell built-in. So if I type in type cd, it says cd is a shell built-in, right? So then you know, okay, I got to go to help. If I do type ls, I see that ls is an alias, and an alias is basically means whenever I run ls, automatically add this here. So this special argument that adds color to my results, right? Because I like color on my terminal. But then I can do things like which ls, right, and figure out where that is in terms of where the executable binary is located. So with all these pieces, we start to kind of get a way to systematically look at documentation for Unix, both shell built-ins and any sort of executables you might be running through the shell. Since I don't have as much of a time limitation, I want to mention also info. So info here under the section deeper down the rabbit hole, info is a separate documentation system, which is completely distinct from the man pages and different than the lineage of the Unix programmer's manual that I mentioned before. So man pages are the descendant of the Unix programming manual created by the developers of the Unix operating system. Info is a documentation system that that the GNU project and Richard Stallman have advanced as a better alternative to man pages. And in my opinion, I would say that while there are some technical advantages, really that it hasn't really caught on. So the main advantage here is man pages are written in order to optimize for being printed out on hard paper. And info pages actually have hyperlinks in here. So as I hit tab, you can see that I'm advancing from hyperlinks. And if I hit enter on any of these, it actually opens up that hyperlink. And I can hit L to go back. So it's sort of like a text-driven browser here. And yeah, there's some advantages there. But generally, like man pages have pretty much all the documentation, and things are very sporadically documented inside info. So for the most part, I would just say ignore info, forget that it even exists, and just focus on man pages. Other people might have different opinions on that, though. So at this link, I've got a tutorial to basically follow up everything I talked about man pages and get a little bit more practice developing some of those muscle memories. And I'll just show you what that looks like. So here, this is a markdown file that I have posted on GitHub, and I talk about history. I've got some interesting links. And I talk about, I walk you through some of the different ways to run these commands beyond what I just showed you. And I want you to basically go through and follow along and type all these commands. And when you see any of these questions here, take a moment and try to kind of think about what I'm asking. So like what might be the advantage of stir n lane over stir lane? Like that's a question that you can answer by looking up things inside the various man pages and kind of reading the contents in there. I've got some comments about how to do more advanced searches here, including searching specific sections, and how to do more advanced full text searches as well. Like you can actually search not just kind of the header and the title of a man page, but the full text, and it takes a little bit longer, but sometimes that's useful. So go through this and give a shot on all these different questions here. Yeah, like for example, try to search for any man page that mentions Richard Stallman. I think that's a fun exercise. And when you're through with that, I'd like you to move on to a C programming practice. And this practice is basically going to give you a chance to write an abstract data type. This is basically working on a linked list. And the instructional team assumes that all of you have had experience with linked lists before, so I'm just going to very quickly hit the main points here. So a linked list is a dynamic data structure, and it achieves its dynamic nature by basically chaining together separate nodes through pointers. And there's some pros and cons to that. I mean, a pro is it's very easy to grow a linked list. You just have to allocate a new node and then add it to the chain of pointers. And you can also very easily manipulate those pointers to do things like reorder the nodes or sort and things like that without having to necessarily copy the full data of the contents of the node. To think about like a static array, for example, if you were to grow a static array, you have to call something like a realloc. And a realloc is a libc function that essentially allocates a larger static array and then has to copy all of the contents of the existing array into that new array. And you can imagine, copying a large array is computationally expensive. So linked lists are cheaper to grow, and they can generally grow a little bit more granularly node by node. That's a pro. The con is because everything is connected by pointers, you experience what's called pointer hopping as you advance through the linked list. And that really has to do with having poor data locality, because when you allocate all these different nodes, they could be scattered all over memory, right? So there's very poor data locality. And for things like caching, like you just end up having a lot more cache misses, which can really slow down your code. Another just kind of functional problem is you don't have an index, right? So with an array, you can index into the array to get a particular element. With a linked list, you can't do that. So if you want to get the 20-second element, you've got to walk through starting from the front or the head or the first node, and then walk pointer by pointer by pointer until you get to that 20-second node, which is a bummer. And this is essentially what a singly linked list looks like. We've got these pointers for head and tail, and then we have these individual nodes that have some data, and they've got a pointer to the next thing. And chained together kind of looks like that image on the bottom. A doubly linked list essentially adds a previous pointer to each of these nodes, and that ends up basically having some advantages for being able to insert values in the middle of a linked list. So that's just kind of a brief overview of some of the aspects of a linked list. Like I said, we expect that you've worked with these sorts of things in the past. And so this is really just intended to give you a little bit more practice writing an abstract data type and refreshing your C skills. The exercise I've structured uses Unity, a unit testing framework. And I've flushed out the unit tests for this. So basically you're going to get all these unit tests and they're going to be failing. And it's up to you as the author to write the code that's necessary to get them to pass. Unit testing frameworks are used in industry a lot. So usually folks don't write with kind of a raw assert, which is kind of the base libc way of doing testing. Usually you've got a unit testing framework with richer assertions and all sorts of other advanced features that you use instead. And we're not going to be using unit testing frameworks again throughout the rest of this course, but I just wanted to give you exposure to that. So it's not unfamiliar when you work in projects in the future. And so I'm going to pull up the lab that you're going to be working in. So this is a GitHub Classroom project, and here's the repo that you basically are going to be cloning in order to work on this. And so I'll post a link, and it's going to be different from what you see here, but it will clone a repo for you to work in and potentially save your work. This isn't graded. This is just a chance for you to get some practice here, but we do use GitHub Classroom. So again, we've got some general linked list information here. But inside of the repo, we have a test directory, and inside that test directory, we've got vendor, and vendor contains the header file for the testing framework Unity, And we also have this C file, test_device_list.c. And this includes all of the unit tests that I've written for you. So we're importing the unit testing framework. We have set up and tear down functions. And these are kind of magical life cycle functions that run before and after each unit test. I have some utility functions I've created to make it just a little bit easier to run these tests. And then finally, starting with the functions that have a ignore and then an assert. These are the tests themselves, right? So all these. And then here in the main function, this is the entry point for the test binary that you're going to be building. We can see that we're actually calling a special macro to run all the tests through our framework. So a couple of things you're going to hit when you work on this. First, if you compile, you're going to get all sorts of linking errors. And if you're not familiar with seeing linker errors, it can be pretty disorienting. And the reason for that is we have all these tests, and they're calling all sorts of different functions here. So device list push, for example, device list unshift. And the issue, well, I'll navigate a way to kind of show this, is that in the repository right now, we have basically a function definition. Am I using that right? I mix up definition and declaration sometimes. We've got a function defined, function name, and the parameters and types that are going in, and the parameter and the data type of the return type. But this function doesn't actually have a body anywhere. So, and that's because you've got to write it. So here in device list.c, it's empty, right? You've got to implement all of these things in the header. And the problem here is if I go back to our test, so our test device list.c has a bunch of unit tests that try to call these functions, but the symbols of those function names don't actually exist in the binary until you write them. So that's why you get those linker errors. And the way that you get around that is really by commenting out some of these unit tests. So like, again, right, you can take like all these, select all of this, and just go ahead and comment those out. And also be sure to do the same here. And then as you start to implement functions, for example, the device list create is probably the first one you're going to want to implement. You can uncomment the top thing here, the top test, go up to the test function, uncomment this here, and then also be sure to remove this line here that says test ignore, because this actually will not run the tests until that is deleted. So once you have all that done, the test is going to execute, but only for device list create. And you can go ahead and implement device list create and then make sure that you fulfill all the specs to get the unit test to pass. And then you basically move from the top down. So yeah, so that's basically the best way to kind of work on this project. One other thing I've seen students struggle with is here in source we have a device.h and we have a device list.h, and that can be a little confusing. So in device.h we have a struct here, and this emulates essentially a device that you would see in a Unix file system. It's got a major and a minor device type, and these are the things that basically uniquely identify a device, major and minor. Here in device list.h we have something that's different. It's called a device list node, and it's got a pointer to a device. So don't confuse a struct device with a struct device list node. You can kind of think of the device list node as the envelope that you have to wrap the struct device in order to make it a part of the linked list, right? So this contains a pointer to the device, and then it has these additional pointers that we need to be able to string together the linked list. So don't confuse those things, and be very careful with what you're assigning to these different pointers. Since these are typed, it's going to protect you a little bit here, But generally in the future, when you work with things like linked lists, the data is not going to be typed here. This is going to be like a void star pointer. And so it's a lot easier to accidentally assign the wrong thing there, and the compiler's not going to be able to help you. So we just want you to get a little bit more practice with all of this. And please let us know in the Around the World channel if you have any problems getting any of this running. And good luck with everything. Thank you very much.